let's talk about how animals fit into an ecosystem and this concept of food webs and what exactly that means. So first of all, let's remember that all animals are heterotrophic, meaning that they eat other things. Plants and photosynthetic bacteria or protists, those are autotrophic, meaning that they make their own food. Photosynthetic organisms, all autotrophs, are classified as producers because they produce the sugars that other organisms rely on for energy. And those other organisms, of course, are the heterotrophs. Heterotrophs can be animals, but also fungi and non-photosynthetic protists. And because they consume the things made by producers, they are considered consumers. They consume the sugars. Okay, so we've got the producers making the sugars, the consumers consuming the sugars. This organization of producers and consumers gives us food chains. And you've learned about food chains undoubtedly, where, the small fish eats the algae and then the big fish eats the small fish. And that is a rather simplified version of how things really work. And in biology, we call it we call these things trophic levels. Trophic meaning to eat. So the producers are the lowest trophic level. So here is a food chain in a lake. So the green algae, which is a photosynthetic protist, is the producer, the lowest trophic level. The algae is eaten by snails, which are part of phylum Mollusca, which is a primary consumer. Then the snails are eaten by a small fish, the slimy sculpin. That's a secondary consumer because it's eating the primary consumer. And then the top level is the tertiary consumer, or we sometimes call it the apex consumer, or sometimes we call it an apex predator. Specifically, an apex predator is a predator that doesn't have anything that eats it. Okay, an apex predator eats other animals, but is not prey for anything. So this is a really basic food chain, but it's a little oversimplified. So a food web is going to be a little more complicated. But first, let's talk about energy. Remember that all chemical reactions produce heat. And we learned that way back at the beginning of the semester when we were talking about chemistry. Remember, all some absorb more heat than they release, but all release some heat. In biological organisms, every time we break down big molecules into smaller molecules, heat is released. That's one of the reasons that your body gets warm when you're exercising, because your body is then doing a lot of chemical reactions and producing a lot of heat. Now, as consumers consume at lower trophic levels, some of that energy is lost. So the energy that you eat from, by eating, say, a hamburger, some of that energy goes into your body and stays in the tissues of your body, making up you. But a lot of it is lost in heat and then in, powering the chemical reactions that you do. So as we go from one trophic level to the next, most of the energy is lost. So here's a graph that shows what that means. So here's a trophic cascade in Florida, in, I guess, a swamp or something. So we have producers, we have lettuce, we have eelgrass, and we have diatoms, which are protists. They're producing, or they contain this huge amount of energy, more than 20,000 kilocalories per meter square per year. So if you think of a square on the ground, a meter on each side, each year that space is going to produce more than 20,000 kilocalories of energy. The next level that's going to the primary consumers that are going to eat those producers are going to produce less than, or going to contain, less than 5,000, maybe like 4,000, 3,500 kilocalories in that same space. And then as we go higher and higher, each level contains less energy. So this big amount of energy at the lowest level gets lost as we go up the level. That's why some people argue that having a vegetarian diet is better for the environment, because you're eating this energy here rather than feeding this energy to a cow and then eating the cow. Okay, less energy is lost in the process. Okay, so a food web is a way to describe a food chain, but show more of the complexity of the system. Because in most environments, organisms operate on more than one trophic level. Aside from producers, most things aren't just a consumer. So a food web is able to show that interaction. So here's an example of a food web from your textbook. We've got two colors of arrows. One arrow is showing the energy going up the trophic level. So we have the squirrels, the mice, the little house finch, and the beetle all eating the grasses. So the grasses are the producers. Their energy is going to these primary consumers. The beetle can then be eaten by a spider or a centipede, and those could be eaten by a robin, or a toad, or the beetle itself individually could be eaten by the toad or maybe a frog. Sorry, I don't know which one, or the robin. So, is the spider a secondary consumer, or is the robin a tertiary consumer? Well, it can be prey for the owl or the snake. So you can see that in this, we're showing how one organism can act at different levels, but also be prey for different things and itself be a predator of other things. Okay. Now, the brown arrows show these organisms after they die being food for the decomposers in the soil. That would be fungus and microscopic worms and large worms and bacteria and things like that. So this food web doesn't just go up in trophic levels, it also comes back down to the decomposers that then recycle all of those chemicals and nutrients that were in these biological organisms. Okay, so we've got the grasses as the producers, the squirrels, mouse, finches, primary consumers, secondary consumers here, but these are also kind of secondary. These are secondary consumers, but maybe these are also it gets to be very confusing, right? So if we step aside from these primary, secondary, tertiary labels and we just say producers and consumers, then it allows a little more complexity. And then we have to add in the decomposers, okay, which are really important because they recycle the organic nutrients back into the soil so that they can then be used by the producers to make more producers. Make sense? All right, there is one bad thing about all of these trophic levels, and the fact that some organisms eat other organisms that eat plants, and that is the role of toxins in the environment. So, a lot of toxins can be stored in an organism's body. Not usually water-soluble toxins. They tend to be flushed out by broken down by the liver of animals at least, and flushed out by the kidneys, or just flushed out as water moves through the organism. But fat-soluble toxins often get dissolved into the fats in an organism's body and then get stored with the fat that's stored in the body. This is really common in fish, birds, and mammals. So here we have, again, another food chain where we have the phytoplankton, our photosynthetic producer here on the bottom. Phyto meaning plant, and plankton just meaning something that floats rather than can swim against a current. There's an actual definition of what plankton is. And then we have a mussel that eats the plankton, an amphipod that probably eats plankton and maybe a mussel. And then we have this chain of several different fish that can each eat the smaller fish, as well as the amphipod and the mussel. And what we see is that as the size of the fish increases and as the fish's place in the trophic cascade or the trophic level increases, you get more of a toxin, in this case PCB, in that animal's flesh. And so that's why you may have heard you shouldn't eat too much tuna, because tuna has mercury in it. And that's correct, because there is a lot of mercury in the environment and it builds up in the ocean. And a tuna is an apex predator. So the tuna gets all of the mercury that was in the animal it ate, and the animals that animal ate, and the animals that animal ate. They all get stored in the tuna, even though the energy from those organisms didn't all get into the tuna. The mercury, because it was stored in the tissues, does get stored in the tuna. I said that very eloquently, didn't I? So that's what I wanted you to understand about food webs, about how everything is related and the action of every organism affects every other organism. And of course, the actions of humans can affect the environment, even when we don't realize it, because we don't realize that mercury is building up in the environment until, now our tuna has mercury in it. All right, so that's that section. Next, we're going to talk about one more way that humans affect their environment.